this is lecture 30 of the subject analog circuits. In this class I am going to discuss active high pass filter and active band pass filter. Contents are first order HPF, that is high pass filter, first order high pass filter. Then we will discuss about second order high pass filter, after that wide band pass filter and narrow band pass filter. So, before starting the high pass filter, just go through lecture 29 of this subject. In that class I had discussed the first order low pass filter and second order low pass filter. So, there I had discussed about active filters and passive filters also. I had given the introduction of active filters and passive filter. The advantage of the active filter is it provides gain, and another advantage of active filter is there is no loading effect. There is no loading effect. The reason is that in general in active filters we apply the input signal at the non-inverting terminal of the op amp. That means we use non-inverting configuration of op amp, non-inverting configuration of op amp. When we use non-inverting configuration of op amp, in that case the input impedance is very high. That is the advantage of the non-inverting configuration over inverting configuration. In that case the loading effect is minimized in non-inverting configuration. So, the advantage of active filters over passive filters are it provides gain and there is no loading effect. It is called active filter because in active filters we are using active element, that active element is transistor. In our case that active element is operational amplifier, and basically this operational amplifier, it is made up of transistors, and along with op amp we are using resistors and capacitors to design active filters. So, there are 4 kinds of active filters. Out of those 4 filters I have already discussed about the low pass filter. Now, coming to the high pass filter. So, starting with the first order high pass filter, in the last class we had studied the first order low pass filter. So, we can easily design, we can easily understand the first order high pass filter. What we need to do? We just need to interchange the position of R and C, resistor and capacitor, and those resistors and capacitors are frequency determining resistors and capacitor, right. What does it mean? In high pass filter we can see that this C and R, it provides the filter function, it provides the filter function, it decides the frequency, it decides the cutoff frequency, and the role of this R1 and RF is it provides gain, it provides gain. So, in first order low pass filter the only difference is that this R and C positions were different. In high pass filter, in first order high pass filter, just interchange the location of this C and R. In low pass filter, in the first order low pass filter, if you interchange the position of R and C, it becomes the first order high pass filter. So, this is the circuit of first order high pass filter, right. We can see that this input signal V in, it has been applied at the non-inverting terminal of the op amp. So, it is a non-inverting configuration, RL is the load resistance. Now, we can calculate the transfer function of this first order high pass filter. So, to calculate the transfer function of this first order high pass filter, what we can do? Firstly, we should find out the value of the V1 voltage, that V1 is the voltage at the non-inverting terminal, fine. So, what will be the value of V 1? By voltage divider, this V 1 will be equal to R upon R plus the impedance of this capacitor C, that impedance is 1 by SC. This is the value of V 1, and we had derived the expression of the gain for non-inverting configuration in earlier classes. That expression is V naught upon V in is equal to 1 plus RF upon R 1, but this V in is V 1 here, because V in is the voltage at the non-inverting terminal there, but in this circuit at the non-inverting terminal the voltage is V 1, right. So, basically V naught upon V 1 is equal to 1 plus RF upon R 1. So, do not be confused here, this V in is here the input signal that has been applied, and V 1 is the voltage at the non-inverting terminal. Fine. Let us say this is equation 1 and this is equation 2. Now, you can put the value of V 1 from equation 1 into equation 2, and we can rearrange the terms, and we can find out the value of V naught upon V in easily, right. So, after rearranging the terms, what we get? V naught upon V in is equal to AF into F by FL upon under root 1 plus F by FL square. What is AF? AF is the pass band gain. AF is the pass band gain. It is 1 plus RF upon R 1, and FL is the cutoff frequency, and this cutoff frequency is 1 upon 2 pi RC. So, these things we had done in the case of low pass filter also. So, in the low pass filter the cutoff frequency was 1 upon 2 pi RC, in the high pass filter again it is 1 upon 2 pi RC, right. So, this is the transfer function of the first order high pass filter. Now, we can draw the frequency response of the first order high pass filter. That frequency response is the graph between frequency versus gain. So, in case of high pass filter, the signal is attenuated at low frequency and the signals are passed at high frequencies, right. So, the frequency response is like this. Here we can see that this is the stop band and this one is the pass band, and the maximum gain which we are getting is AF. The maximum gain is AF, and in stop band we can see that the gain is very less. So, it means that the signal is being attenuated, and the cutoff frequency is this FL. This FL is the cutoff frequency, that is also called minus 3 dB frequency. It is also called corner frequency, it is also called break frequency, all terms are same, fine. And the rate at which this gain is reduced, that rate is 20 dB per decade for the first order high pass filter. For the second order high pass filter, it will be 40 dB per decade. So, we can see that everything is same in the first order high pass filter if we compare with the first order low pass filter. The only difference is this position of R and C are interchanged, right. So, the design methodology of the first order high pass filter, it is similar to the first order low pass filter. So, let us quickly review it. Design of first order high pass filter. Again the first step is we design any active filters for a particular cutoff frequency. So, we should know that what cutoff frequency we want, and what is this cutoff frequency? This cutoff frequency is the frequency at which the gain is reduced by 3 dB of the maximum gain. So, the first step is we should know that what is the cutoff frequency. Normally it is given in the question. Second step is we consider some value of the capacitor. Normally we consider the value of the capacitor less than or equal to 1 microfarad. We can take any value of the capacitor less than 1 microfarad. Normally we take the value of the capacitor that is of the fixed value and that is available in the market. For example, 0.01 microfarad, 0.1 microfarad, 0.0047 microfarad, right. And with the help of this capacitor C, we can calculate the value of R. R is equal to 1 upon 2 pi FL into C. FL we know from step 1, C we know from step 2, and in step 4 we can determine the value of R1 and RF from the passband gain. We know that the passband gain is 1 plus RF upon R1 because we are using the non-inverting configuration, fine. So, passband gain is given in the question, normally it is given. If it is not given, then we need to consider some value of AF, right. And then after that we consider some value of R1, normally it is less than 100 kilo ohm, and with the help of this R1 and AF we can calculate the value of RF. And lastly, we need to design the first order high pass filter and mention all the values of the components which we have find out from step 1 to step 4. So, this is the problem based on the first order high pass filter. We have to design a first order high pass filter at a cutoff frequency of 1 kilohertz. So, the cutoff frequency is 1 kilohertz, it is given in the question. Second step is we can consider some value of C less than 1 microfarad. Let us consider C is equal to 0.0047 microfarad, or we can consider 0.01 microfarad. So, any value we can consider less than 1 microfarad, but normally we take the fixed value of the capacitor which is available in the market, fine. So, we are considering C is equal to 0.01 microfarad. With the help of C, we can calculate the value of R, that is 1 upon 2 pi FL into C, and the passband gain AF is given in the question, it is 2. This 2 is equal to 1 plus RF upon R1. From here what we get, RF is equal to R1. Let us consider RF is equal to 10 kilo ohm. So, this R1 will be 10 kilo ohm, fine. This R1 will be 10 kilo ohm, fine. And the last step is to design the circuit and mention all the component values which we have calculated from step 1 to step 4. So, what is the circuit? This one is the circuit, and in this circuit we can see that when we are considering C is equal to 0.01 microfarad, then R is equal to 15.9 kilo ohm. So, to use this 15.9 kilo ohm resistor, what we are using? We are using 20 kilo ohm potentiometer, and with the help of that potentiometer we are setting the resistance value equal to 15.9 kilo ohm, and the value of R1 and RF is 10 kilo ohm, that is mentioned in the circuit. So, these are the design steps which are similar to the first order low pass filter. Now, coming to the second order high pass filter. In the second order high pass filter, again we can design this second order high pass filter just by interchanging the R and C in the second order low pass filter. So, we can see that the circuit is same as second order low pass filter, R1 and RF are same. Now, just this C2 and C3, R2 and R3, these positions are interchanged. If we interchange these positions in second order low pass filter, what we get? We get second order high pass filter, fine. Again we can see that this input signal is applied at the non-inverting terminal, So, again the passband gain AF, it will be equal to 1 plus RF upon R1. If we consider this is node A, this is node B, node A and B, and just apply KCL at node A and node B, and after rearranging terms and just calculate V naught upon V in, then after calculation we get V naught upon V in, that is equal to AF upon under root 1 plus FL by F to the power 4, where AF is equal to 1 plus RF upon R1, right. So, this is the transfer function, this is the gain of this second order high pass filter. So, first order high pass filter can be converted into second order high pass filter simply by using an additional RC network. Both are same thing in fact. If we are using 2 RC sections, it becomes second order filter, right. And or we can say that in the second order low pass filter, if we interchange R and C, then it becomes second order high pass filter, fine. One more thing, when we consider Butterworth filter means which gives the flat pass band. Butterworth filter means which gives the flat pass band. What is this flat pass band? Flat pass band means when we draw the graph between gain versus frequency, then in the pass band the gain should be flat, gain should be constant, but this is for low pass filter. For high pass filter, when we draw the graph between gain versus frequency, then the graph is like this. This is your pass band, this is stop band. In the pass band, the gain should be constant, it should be flat, and we get this flat pass band when AF is equal to 1.586. When AF is equal to, when we take AF is equal to 1.586, then it gives Butterworth response. So, in general, when nothing is given in the question, then by default we consider Butterworth response, and when we consider Butterworth response, Butterworth filters, then we take AF is equal to 1.586, and when we draw the frequency response of this second order high pass filter, that is the gain versus frequency, then the graph is same, just the rate at which the gain is reducing, that rate is 40 dB per decade, 40 dB per decade, fine. And the design of second order high pass filter, it is similar to the second order low pass filter. What does it mean? Again we will start with FL, then after FL again we will select some value of C, that is less than 1 microfarad. With the help of C we will calculate the value of R. So, what is the cutoff frequency in case of second order high pass filter? It is 1 upon 2 pi under root R2 R3 C1 C2. Let us see the circuit again. We are taking here C2 and C3. So, the cutoff frequency, it will be, the cutoff frequency will be 1 upon 2 pi under root R2 R3 C2 C3. Normally we take R2 equal to R3, C2 is equal to C3. When we take it, then FL becomes equal to 1 upon 2 pi RC, fine. So, the step 1 is to find out the FL. In fact, FL is given. We design this, we design the filter for a particular value of cutoff frequency, for a particular FL. Then we take the value of, we consider some value of C, that is less than 1 microfarad. Then we calculate the value of R2 R3, and this C means C2 is equal to C3 is equal to C, and here we take R2 equal to R3 equal to R. For simplification purpose, it would be better, because if we take it, then equations are simplified, and also we are getting the same cutoff frequency, right. In step 4 again we calculate the value of R1 and RF, and again we take AF is equal to 1.586 for Butterworth response, and the last step, in the last step just design the second order high pass filter and mention all the component values, fine. So, if we are taking C is equal to C2 equal to C3 is equal to C, that is 0.0047 microfarad, then R2 and R3 will be equal to 33 kilo ohm, fine. And similarly, when we take the value of R1 27 kilo ohm and AF equal to 1.586, then we get the value of RF, that is 15.8 kilo ohm. For that we will be using a potentiometer. Fine. So, the steps are same for the second order filter, second order high pass filter as in second order low pass filter. So, the next is the band pass filter. So, I have already given the introduction of band pass filter in earlier classes. So, band pass filters are of two types, wide band pass filter and narrow band pass filter. Wide band pass filter means Q is less than 10, narrow band pass filter means Q is greater than 10. Q is the quality factor and Q is defined as FC upon bandwidth, where FC is the center frequency. This FC is equal to under root FH into FL, and the bandwidth is defined as FH minus FL. FH is the upper 3 dB frequency, FL is the lower 3 dB frequency. When we draw the frequency response of the wide band pass filter, that is the gain versus frequency, then the graph is like this. So, it is called band pass filter because it passes a particular band of frequency and rejects the remaining frequency. So, here we get two cutoff frequency, one is FL and another one is FH. This rate is your 20 dB per decade, 20 dB per decade, and this one is minus 20 dB per decade. This is the pass band gain, that is the maximum gain, that is the mid band gain, and the bandwidth is FH minus FL. FL is the lower 3 dB frequency, FH is the higher 3 dB frequency, fine. And we can easily design the wide band pass filter just by cascading the first order high pass filter with first order low pass filter. Now, we all are familiar with both the filters, first order high pass and first order low pass. So, this is the first order high pass filter, and the output of the first order high pass filter is connected to the input of the first order low pass filter. So, I have already discussed about the first order high pass and first order low pass, and the overall order of this wide band pass filter is 2, and the minimum order required for a wide band pass filter is 2. We cannot design the first order band pass filter, right. So, these things I have already discussed in the earlier classes, fine. So, we can easily design the wide band pass filter here. For that, some value of FL will be given, some value of FH will be given, fine. This FL is the low cutoff frequency of high pass filter, this FH is the high cutoff frequency of the low pass filter, fine. And we have already seen that how we can design a first order high pass filter and first order low pass filter for a particular cutoff frequencies. So, the design steps are same. So, we can easily design this wide band pass filter, and we can calculate the transfer function of this circuit also. For that, we know that since both the filters are in cascade, so the overall gain of this filter, it will be the gain of the first order high pass into gain of the first order low pass, fine. So, what will be the voltage gain of this wide band pass filter? It will be mod V naught upon V. So, the gain of the first order high pass filter we have already calculated, AF into F by FL upon under root 1 plus F by FL square. Let us say this is AF1 into the gain of the first order low pass filter, that is, let us say it is AF2 upon under root 1 plus F by FH square, fine. So, this is the gain of the first order high pass filter, this is the gain of the first order low pass filter. We have just multiplied it, fine, because both are in cascade, fine. So, this is the gain equation for the wide band pass filter, right, and we have already derived these equations for the first order high pass and first order low pass. So, coming to the next filter, that is the narrow band pass filter. In narrow band pass filter, we use multiple feedback. And in this circuit we can see that we are using the inverting mode, inverting configuration, because this input signal has been applied at the inverting terminal and it is having multiple feedback through R3 and C2. For this narrow band pass filter, the design equations are R1 is equal to Q upon 2 pi Fc into C into AF. Q is the quality factor, Fc is the center frequency. Similarly, for R2, Q upon 2 pi Fc into C into 2Q square minus AF, and R3 equal to Q upon pi Fc into C, where AF is equal to R3 upon 2 R1, and this AF is the gain at the center frequency. Center frequency is the frequency at which we get the maximum gain, fine, and this center frequency is under root FH into FL. That means under root upper cutoff frequency into lower cutoff frequency. So, in narrow band pass filter the bandwidth is less, that is why it is called narrow band pass filter. Normally we say that for narrow band pass filter the quality factor Q is greater than 10, fine. So, these are the design equations for narrow band pass filter. By just selecting the proper value of R2, R3, R1, R2, R3, we can design the narrow band pass filter to get a particular center frequency at which the gain is highest. This is the reference.